Often in business, we want to use time series data to predict the future value of an important variable. If the time series is stationary, that is, if the time series exhibits a horizontal pattern without trend, seasonal effects, or cyclical effects, exponential smoothing is an appropriate forecasting method. A gasoline distributor wants to use its sales of gasoline in recent weeks to predict the number of gallons it will sell in future weeks. This will enable the distributor to better anticipate demand, which will allow it to reduce the likelihood its supply will be insufficient to meet its demand. This in turn will increase customer satisfaction and then potentially result in higher profits for the gasoline distributor. Sales for the past 12 weeks have been collected. Consider the 12 weeks of data in this table. These data show the number of gallons of gasoline in thousands sold by a gasoline distributor in Bennington, Vermont over the past 12 weeks. For these data, Y sub t is the number of gallons of gasoline sold by the distributor in week t. We see, for example, that Y sub 1 is 17, and Y sub 9 is 22. This means that the distributor sold 17,000 gallons of gasoline during the first week and 22,000 gallons of gasoline during the 9th week of this time series. The gasoline distributor would like to use the patterns that can be identified in these recent gasoline sales data to predict its gasoline sales for future weeks. Here we see a time series plot for the sales data. Note how the data fluctuate around the sample mean of 19,250 gallons. Although random variability is present, there does not appear to be a trend, a seasonal pattern, or a cyclical pattern in these data. This time series appears to be stationary, so application of the exponential smoothing method of forecasting is appropriate. We will now use Excel and an exponential smoothing model with a smoothing constant of 0.2 to generate forecasts for these gasoline sales data. The data for this problem have been entered into columns A and B. The weeks in which the gasoline sales were made are in column A, and the gallons of gasoline sold in thousands for each week are in column B. Now we enter the label Forecast in cell C1, next we click on Data in the ribbon, then click on Data Analysis in the Analyze tab. This opens the Data Analysis dialog box. When the Data Analysis dialog box appears, select Exponential Smoothing. Then click on OK. This opens the Exponential Smoothing dialog box. Now enter B1 to B13 in the Input Range box. Enter 0.8 in the damping factor box. This indicates that we are using a smoothing constant of 0.2. Now click on Labels to indicate the first entry in the column that contains the time series is a variable name. Then enter C2 in the Output Range box and click OK. Excel generates the forecast value for each week and outputs the results to the corresponding cells in column C. Let's consider how well our exponential smoothing model predicts sales for the weeks in our time series. First, we must calculate our forecast errors for weeks 2 through 12. We enter the label Forecast Error in cell D1. In cell D3, we enter the formula equals B3 minus C3. This is the actual sales for week 2 minus the forecast sales for week 2, or the error the exponential smoothing model with a smoothing constant of 0.2 made in forecasting week 2 gasoline sales. Then copy the formula in cell D3 into cells D4 through D13. We can use these forecast errors to find the mean absolute error, the mean squared error, and the mean absolute percentage error for this model. To calculate the mean absolute error, we must find the absolute value of each of the forecast errors, then find the mean of the absolute values of the forecast errors. To do this, we enter the label absolute value of forecast error in cell E1. Then use Excel's absolute value function in cell E3 to find the absolute value of the forecast error for week 2. And copy the formula in cell E3 into cells E4 through E13. Finally, we use Excel's average function in cell E14 to find the mean of the absolute forecast errors for this model. The value 2.596 in cell E14 is the mean absolute error for our exponential smoothing model with a smoothing constant of 0.2. To calculate the mean squared error, we must find the square of each of the forecast errors, and then find the mean of the squares of these forecast errors. To do this, we enter the label squared forecast error in cell F1. Then enter the formula equals D3 squared into cell F3. And copy the formula in cell F3 into cells F4 through F13. Finally, we use Excel's average function in cell F14 to find the mean of the squared forecast errors. The value 8.982 in cell F14 is the mean squared error for our exponential smoothing model with a smoothing constant of 0.2. To calculate the mean absolute percentage error, we must divide each forecast error by the actual value of the time series for the same period, then multiply each of these values by 100. We then find the absolute value of these results and find the mean of these absolute values. To do so, we enter the label percentage error in cell G1. And enter the formula D3 divided by B3 times 100 into cell G3. And copy the formula in cell G3 into cells G4 through G13. We then enter the label absolute value of percentage error in cell H1. And we use Excel's absolute value function in cell H3 to find the absolute value of the percentage error in cell G3. and copy the formula in cell H3 into cells H4 through H13. Finally, we'll use Excel's average function in cell H14 to find the mean of the absolute percentage errors. The value 13.402 in cell H14 is the mean absolute percentage error for our exponential smoothing model with a smoothing constant of 0.2. We can now use the mean absolute error, the mean squared error, or the mean absolute percentage error to compare our exponential smoothing model with a smoothing constant of 0.2 to other possible forecasting models for the gasoline sales time series data.